Start. Welcome back. So for today, I'll give some indication of various ways of seeing that these theta functions are modular, and then outline some variations in further directions, most of which I think I listed in the outline. So the use of theta functions instead of thinking of, okay, any theta function is modular form, well, maybe any modular form you're interested in can be obtained from a theta function, at least if you're interested in finding its explicit Q expansion, and it turns out that this actually gives, in many cases, quite fast algorithms for computing these Q expansions out to some distance. There's the use of Poisson summation formula, which was our main tool for obtaining and proving these modular forms and studying them, also in other contexts to get sphere packing bounds. There is this suggestive and fruitful analogy between theta functions of lattices and weight enumerators of linear codes. And finally, there is higher theta functions, Siegel theta functions, and other variations, and questions about how far can one apply the same techniques that we have been using in that context. Okay, so why is theta modular? So again, this is for any lattice for which the quadratic form goes to the rational numbers, positive definite. And we saw already that it was enough to consider the case in which we are dealing with a theta function of a lattice, well, the dual of a lattice, in fact, with respect to some periodic times harmonic weight with alpha star being periodic with period L, where L is some lattice which is integral, in fact, is even. So in particular, it's contained in L star. And so what happens there is, if you fix L and therefore L star and P and let alpha vary, this is a finite set, so we have a vector space with these theta stars, these theta of L stars, generate, as we vary alpha, generate a vector space V of finite dimension, in fact of dimension less than or equal to, usually less than, the index of L and L star, which is to say the discriminant. And then we can study the action of the full modular group, PSL2Z, on V by using the fact that it's generated by two transformations, T, which is just tau to tau plus 1, that acts on V because each coset here of a lattice, of an even lattice in its dual has constant norms mod 2, so translation by 1 multiplies each one of these generators by some constant, and then S, which takes tau to minus 1 over tau, acts on V because of Poisson. And so this gives us a map from here to linear transformations of V, and what we want to show is that the kernel of this map contains some congruence group gamma of n, because once that happens, we will have a representation, or we'll have modularity, well, we'll have a representation of the quotient, and we'll have modularity of all of these theta functions at once for that congruent subgroup. Notice here that I am suppressing, well, for T I don't need to suppress anything, but for S, and therefore for everything else, I'm suppressing those epsilons and those C tau plus D's So the action already is, modulo these multiplier systems and factors of theta plus d to the n over 2. At any rate, so we want to construct this n. In fact, I can tell you more or less what n is. If I remember correctly, n just turns out to be the exponent of this quotient group. So if L is even and self-dual, exponent is 1, so it should be modular for the whole group. I believe this is correct. At any rate, so one way to do it is to just exhibit the extension of this map to a map from the quotient gamma mod gamma of n to GL of V. That's a rather painful computation involving various explicit exponentials and Gauss sums, etc. But it's been done once and for all, and so in some sense that answers the question. Notice that even there, we weren't able to prove easily that one of these theta functions was modular without introducing the whole packet of L functions generating the space V for the same pair L star mod L. So that's one way of doing it. And when you actually get this representation, it yet again turns out to be some avatar of a V representation. Another way of doing this is to say, well, remember, I can reduce it to this situation where L star over L, but anytime you have some sublattice that's also therefore going to be even, M star and M will satisfy this. So if you have some collection of sublattices for which you can do it more easily, then it will follow that my original theta function had to be modular as well, albeit maybe for some larger n. And the m that I'm going to use will be the following. M is going to be the span of an orthonormal set, which you can always construct basically by doing Gram-Schmidt, and instead of normalizing things to have unit norm, normalize them to be lattice vectors. And the advantage of that, well, what is the advantage of that? If p equals 1, that is to say, if you aren't concerned too much with our weighted theta functions, you just want to use ordinary theta functions, so for instance, you're concerned with representation numbers under congruence conditions on a quadratic form, but you aren't too concerned about the radial distribution. If p equals 1, then this is really nice because each one of these theta functions, my generators, theta m star alpha, that factors as a product of one-dimensional theta functions. And so that means if you can prove each one of these is modular for some congruence group, that means that the product I started with is modular for the intersection of all of them, which is again a congruence group. So it's enough to do it for one-dimensional thetas. And what happens there is, well, I mean, you still have to, one approach is, well, you can still exhibit this map, but this time V is much simpler than before, because for each one-dimensional lattice, I mean, this is basically writing M as a direct sum of V scaled by some even numbers, and each one of these quotient groups is just a cyclic group of order 2aj, so you have a small space and it's much easier to exhibit your matrices. What's the matter? Oh, sorry. And when you do that, you can reconstruct our original representation on V, or rather on, for V being the span of the theta functions m star alpha, that is going to be then the tensor product of a bunch of representations v1 up to vn. Is that what you want me to do? Okay. It's going to be a tensor product of a bunch of representations, and then my representation that I was looking for here is going to be the tensor product of those representations corresponding to one-dimensional thetas, and that will tell me again what this representation is in that special case, but from that special case I can go back to L and L star. What I've lost in this is that my n might be a lot bigger. It still has to contain the exponent of L star mod L, but I've probably lost quite a bit by going to a box sublattice. However, I can gain most of it back by saying that in this case n is going to be the LCM of 2a1 up to 2an, but anytime I find an orthonormal set, I can play the same game, and so if it's if it's modular for each one of these congruence groups, it's also modular for the GCD of all the n's that I can get that way, and that almost gives the correct n. You are off within some part of 2 usually, but that's almost good enough, and of course if you do want to find the actual if you do want to find the actual n, you can still go back to the arguments with exhibiting GLV explicitly. So that's what we do for the case where p equals 1, but if p is not equal 1, then again, up to the fact that I'm, morally speaking, I have the twisting factors have the extra powers of I to the d in them and so forth, but morally speaking, if p is not equal 1, I still have the same v1 tensor, etc., tensor vn. I can no longer write a general theta function like this as a direct product unless p happens to factor, which doesn't happen very often, but the representation is the same as if I did factor it because my generators of the group act in the same way, and so the whole group is acting the same way. So that is at least one approach to actually deriving the modularity of these. And as soon as you know they're modular, there's all of this wonderful theory about behavior of the coefficients, estimates on modular on cusp forms, etc., Eisenstein theories that you can apply to study representation numbers with congruence and angular conditions, etc. So that's topic 1, and everything from now on is miscellaneous applications, extensions, connections, etc. So hope I have enough time to get to, well, ideally all, at any rate, most of them. So the first one I suggested was this notion of using this computationally. So I hope that we all believe after the past however much it was, 15 minutes, and all the other lectures we heard about theta functions, that if you have any theta function for a rationally, a lattice with rational inner products, any theta is some modular form. And we have this prejudice that even though we know that equal signs are symmetrical, when we have an equation like this, it usually means the thing on the left is what we want to evaluate in terms of the thing of the right, but sometimes it helps to go the other way around and to express a modular form as a theta function, especially if you want to compute it for some reason. So here's an example that turned up in the past few years that I'm aware of, but there are lots and lots of them. So suppose that for some reason you're a number theorist who doesn't care much about quadratic forms, but really cares a lot about twists, special values of twists of L series. So for instance, if E is some elliptic curve, let's say the congruence number curve, this will be what you have to evaluate to tell if you're expecting that curve to have non-torsion points. If you don't know what most or any of that means, that's fine. It's just an example of a question that number theorists are interested in, and it's relevant to us because there is a theorem of Arts-Projet saying, in this case, this is some elementary factor times the q to the d coefficient of some modular form, in this case of weight 3/2, and for this particular case, the weight 3/2 form was determined by tunnel. It is the product of three theta functions in dimension, three theta functions in dimension 1, the square of theta z, and the square of theta of z squared, z scaled by 8, and with some weight, which is just the periodic weight alpha of whatever integer is 1 or minus 1 according as the integer is even or odd. And these theta functions, right, so this particular example is computation of tunnel, and each of these, excuse me? That's for the congruent number curve, right? So so this is for E being the curve y squared equals x cubed minus x, and under some congruence condition on D. That catches half the weights, and the other half tunnel gives a similar formula, but I think one of these theta functions becomes theta of z scaled by 2. The point being, each of these is a really easy power series to write out, and multiplying power series to n terms, I can do using various alternatives for fast multiplication in little more than n multiplies. So that means that after being reasonably clever with the computation, you can compute the first n values in time almost constant per value that you're computing, which is essentially as good as you could hope for. And this O of 1 is really n times some power of the logarithm. And so that's been used to compute these out, to levels that would have seemed fictional, 20 years ago. You can compute the first 10 to the 10th of these coefficients. William-Stein's group is hoping to get at least some of the more famous ones out to literally trillions. Of course, these days trillions don't seem to be such big numbers, but anyway. And then you can, and remember, these have to do the ranks of elliptic curves, and so you can single out the unexpected zeros in those power series and search for elliptic curves of rank 2, 4, etc. in these families. And ultimately, the technique is that you can take a theta function and expand it quickly. And some variations of this, instead of a modular form of weight 3/2, right? So this is weight 3/2. You have other weights, and so you can try to express them either as products of more theta functions or products of theta functions with some, where the number of variables is small, but you have put in some harmonic weight. But there are variations of this technique that can allow you to compute most given modular forms that you're likely to encounter, again in this time, where if you want to compute the first n coefficients, you will get them all in scarcely more than constant time per coefficient. So that's application number 1, and that's all I'm going to say about fast computation, at least above modular forms. Okay, so the same principle that exploiting the symmetry of the equal sign. Let's go back to our old standard, the Poisson summation formula, which says that the sum in n dimensions, it says that the sum of any function, let's say any Schwartz function, over a lattice is equal to the discriminant of the lattice to the power minus a half, which is to say the density of the lattice, average number of lattice points per unit volume, times the sum over dual lattice vectors of the Fourier transform. And I'm going to use this in much the same spirit as the function equation for the zeta function. By the way, remember, this can be used to derive the function equation of zeta and of the zeta function of quadratic forms, etc. In much the same spirit, I'm going to use this as a way to, strangely enough, estimate the discriminant. That is to say, I'm going to choose some particular function v, some particular function f, excuse me. So suppose that for all v in, let's call them x, because they're not lattice vectors, these are x in Rn. And suppose it's true that for all x in Rn, such that the norm is bigger than or equal to the minimal norm of the lattice, by which of course I mean the minimal non-zero norm, it is true that f of v is non-positive. And suppose on the other hand that the Fourier transform, so all x, it's true that the Fourier transform of f at, maybe call it x star, at x star is positive, or at least non-negative. Suppose you do that, then what happens here? On the one hand, you have a sum that is less than or equal to f of 0. On the other hand, you have a sum that's bigger than or equal to the discriminant to the power minus a half times f hat of 0. And that means that the discriminant to the power minus a half, which is to say the density, is bounded below, is bounded above, the discriminant is bounded below, the density is bounded above by the ratio of f of 0 to f hat of 0 for any function f that you can concoct that satisfies these two criteria, that it is non-positive past the minimal norm, and it has an everywhere non-negative Fourier transform. So that means for any such function, all lattices with the same minimal norm have to have discriminant, at least have to have density at most this much. And that is, in fact, an open question for n bigger than 1, just how good can you make this ratio? But we can look for functions, we can just construct them, take Gaussians times polynomials. Anytime you have constructed such a function, you get a bound. And it turns out that we have, who is we in this case? This is Henry Cohn's thesis, part of which is joint work with me. In particular, it turns out that this holds not just for lattice packings, but with an additional argument, you can make it hold for any packing of spheres for which the radius is, well, let's say for which the diameter is equal to the square root of this. And if you just compute what's the best functions you can get, you actually get the best bounds known for, let's say, n between 9 and roughly 36. I have to stop at 9 because for 8 and below, the best lattices are already known. If you just want to do it for unrestricted lattice packings, we actually go as far down as 4. And so, by the way, if you want to play this game yourself, you can assume without making your bounds worse that your function is radial. Because if it's not, you can take the average over rotations of the function and get a radial function that has the same properties with the same inequalities. So you might as well assume the function is radial, so we're just looking to solve essentially some linear programming problem in the infinite dimensional space of functions on the positive real axis. And we don't know how to do it, but again, we can compute. And one remarkable thing that this computation turns up is that we seem to have equality. That is to say, the bound you get seems to be the same as the best lattice that is known in that dimension, therefore the best sphere packing, exactly in the case that n equals 1, 2, 8, and 24, where we get the lattice Z, the lattice A2, the lattice E8, and the Leach lattice. All of these are conjectural, but if the conjecture is true, then for any epsilon, we can prove a bound that's arbitrarily close to the conjectured best density. Now that's not too exciting in dimension 1, even though that's the only dimension we can prove it. It's not very exciting in dimension 2, although the function that we get there is somehow more mysterious than the others. And the reason for that is, if you imagine that you have equality here, then if you trace back this argument, that means the function has to somehow vanish exactly at all the lattice norms, and the Fourier transform has to vanish exactly at all the dual lattice norms. And you can sort of imagine constructing such a function for the E8 lattice, because the lattice and dual lattice norms are just even integers, positive even integers. The Leech lattice, same thing, except you omit 2. The A2 lattice, it's some weird, some weird arithmetic sequence listed in order, and yet if you just do the numerical computation and ask for the optimal function, numerically the zeros find their way to the list of the lattice norms of A2 in increasing order. And we have no idea what this function looks like, but to be honest, we don't have any idea what the E8 and Leech lattice functions look like either. But we have come within 10 to the minus 14 in this case, and within a small multiple of 10 to the minus 30 for the Leech case. And in this case, we isn't really me at all. That extension of the computation was done by the same Henry Cohn and Abhinav Kumar, many of you know and have seen around here this year. And they did that because they needed this to prove that the Leech lattice is actually the best lattice packing. The best lattice packing of spheres of identical bores in R24. It was already known to be locally optimal, and basically it needs to come really, really close and to apply some further clever geometrical tricks with this function and some related ones to show that any lattice that comes close enough has to be close to the Leech lattice in some sense, and then to numerically translate locally close to a number, and that number turned out to be 10 to the minus 30. They also obtained a new proof of the E8 optimality that's essentially different from the Blichfeld and Mordell-Blichfeld proofs, which used reduction theory. So ideally, somebody is going to figure out where these mystery functions in dimension 8 and 24 will come from, and then we will have solved the sphere packing problem in dimension 8 and 24. And since I have a captive audience here, I can't resist pointing out this amazing open problem and hope that somebody here, we have graduate students in all areas of number theory and elsewhere, and lots of people who used to be graduate students. And maybe one of you can make the crucial connection between this and some other bit of mathematics where this function will come from. So that's my second topic. How much time do I have? Oh, good. I might actually finish. Third topic is this remarkably fruitful analogy between lattices, which are particularly nice configuration of points. If they're uniform collections of points, often in connection situations they're trying to figure out which numbers are represented by them, or by the quadratic form, or how good the sphere packing is. And there is an analogy between lattices and linear codes, which are discrete analogs, which are what happens when you try to, so to speak, pack spheres in this discrete Hamming space, which arises naturally in communication theory and elsewhere. And in particular, I'll concentrate on the situation where we have a linear code in V mod 2z to the n. And for once, I do really mean V mod 2z to the n. Let's say I have an n-dimensional space with a chosen basis. And once I have a chosen basis, I have the notion of the weight of a word, which is just the number of non-zero entries. The number of I such wi is equal to 1. In general, it would be such a number of i's for which wi is non-zero. That corresponds to the norm of a lattice vector. And again, this is additive. You can take direct sums and the norms add here, and the weights add there. And the theta function of the lattice corresponds, which is a sum over vectors of q to the power, well, q to the power 1/2, something that's a generating function for the norms. Here we have a generating function for the weights that's usually expressed as the weight enumerator of the code, which is a homogeneous polynomial of degree n in two variables. And so that's equal to the sum over code words of x to the n minus the weight times y to the weight. So each coefficient of this tells you how many words there are of a given weight. And just as we had this Poisson summation formula here, which told you that theta L at tau connects with theta L star at -1/tau, there is this discrete Poisson summation. What usually happens, by the way, this is typical, that working over finite fields is easier than working over the same question over the real numbers, except it's less finite fields or p-adic fields, except it's less familiar, so it takes a while to realize how much easier it is. So for instance, here there's no analysis, it's basically just the algebra of the discrete Fourier transform, and you find that the weight enumerator of xy is equal to some elementary factor, which here is just the power of 2, times the weight enumerator of the orthogonal complement evaluated at x plus y, x minus y, right? So here L corresponds to its dual lattice, here C corresponds to its dual code, and again there are important special cases where, as soon as I find the important special cases, I had this wonderful analogy written out here, and now I can't find the page it was on. Anyhow, I don't think I have enough time to hunt for it among my pages, so I think I'll make this up as I go along. Okay, so you have this this correspondence. In particular, if the code happens to be, if the lattice happens to be self-dual, you can distinguish between even and odd lattices. There's always a shadow. The even lattices are the ones which are their own shadow. And so if it's equal to L, which is also equal to the shadow of L, then this is a modular form, which is a polynomial in E4 and the square of E6, or if you prefer, and delta. And this corresponds to the theorem of Gleason, which is that a doubly even code it's invariant under whole. Doubly even means all the weights are multiples of 4, and just as this required 8 to be a multiple of n, 8 has to be a multiple of n here also, and then the weight enumerator is a polynomial in two basic generators, one being the weight enumerator of the shortest possible of these self-dual doubly even codes, which is the Hamming code, and the second being something of degree 24 that corresponds in some sense to the delta function. In fact, corresponds quite strongly if you believe in construction A, etc. And, okay, you can barely see all of that. Okay, and if you believe that weighted theta functions are useful also, they're useful for telling, given a, given the number of vectors in a shell, how are they distributed within the shell? There is a similar question you can ask over here. Given a number of code words of a given weight, how are the supports of these code words distributed among the n coordinates? And there turns out that there is an analogy of this, WCP. Here, P had to be a harmonic polynomial. And here, for once, the theory is actually a bit more obscure in the discrete situation, but there is a sense of harmonic discrete polynomials that was developed only about 20 years ago by Descartes. And once you have this theory, you can obtain the same kind of results, for instance, showing that if you have an extremal code, and again, extremal makes the same kind of sense here as it does there, then the code words form a t design for some large value of t. In this case, the largest value is 5.5 instead of 11.5. And there are the same analogous kind of questions here. So the extremal lattice for N24 is Leach. The extremal code for Len24 is the binary Golay code. This has also a sporadic automorphism group, just like this one did. Conway 0, okay, it's double cover sporadic simple group. For 48, we have several examples. Here for 48, we have only one example. It's known to be unique. It has automorphisms by PSL2 of 47, like one of these does. And past 48, nobody knows. And just like for lattices, it's one of the long-standing and still open questions in coding theory whether there exists a self-dual extremal code of length 72. But you can use all of these harmonic polynomials, harmonically weighted weight enumerators, to get lots of combinatorial results about, if there is such a code, how many code words of minimal length contain any given set of 5 coordinates, and various things of the same kind, which will look very familiar, at least to the 10 people who have been toiling away at getting these combinatorial results for the minimal shell of the 48-dimensional lattices. I should probably mention here that with the same Scott Commoners, who was one of the undergraduates that were helping me compute the theta function of that other lattice in 72 dimensions, we have now an SL2 style development of these Descartes polynomials. What's that? Are you just asking me to bring the page forward, or is there another question? Okay. So we think now that we have a cleaner development. I mean, we have a development. We think it's cleaner than using the various combinatorial identities that appear very heavily in Descartes and others' uses of these polynomials, and we can use them to get to, well, at least to tighten this analogy a lot further. But at any rate, if for some reason you care a lot more about chords than you do about quadratic forms, even after having spent a week at the Arizona Winter School on quadratic forms, then some of the same techniques will apply there. And finally, I think I still have time for this, higher theta functions. Now I'm sure I do have this written down. Okay, so we have our theta function of a lattice, or maybe a lattice with some weights, and it describes norms of lattice vectors. For example, the number of representations of an integer as sum of however many squares, or the number of vectors of a given length in a lattice. Okay, supposing I want now to describe not single vectors, but pairs of vectors. And to describe the configuration of a pair of vectors, I need to know not just the inner products of each of these vectors with itself, but also with each other. In other words, I want to figure out what the geometry of this triangle is. And now the question is, okay, given a lattice, and given the size of this triangle, how many ways are there to find a copy of this triangle in the lattice, let's say with this vertex being the origin? Okay, so now we need a generating function that, whoops, that was not a good idea. A generating function that encompasses, I need now 3 variables in my generating function because I want a distribution of triples, VV, VW, and WW. Or a nicer way of saying it is I want the distribution of gram matrices of this form, and in the same way that you could, well, I mean, let me put it another way. If you think about this as being a quadratic form. This is a quadratic form, a little quadratic form of rank 2, and we're asking for presentations instead of an integer by quadratic form over some rational number. I'm asking for presentations of this two-dimensional quadratic form by this one. And of course, the representation of an integer is the representation of a one-dimensional quadratic form. But you can do this for 2 or for 3, etc. And so the generating function here, I need 3 variables. It's going to look something like, maybe I'll call it theta upper 2 sub L. And these variables, I guess I label tau11, tau12, tau22, and that will be the sum over all pairs of vectors of the same kind of thing we have seen before, x pi I, except this time it's going to be the norm of v1 times tau1 plus the norm of tau11 plus the norm of v2 times tau22 plus the norm plus the inner product of v1 with v2. Oops, what have I done here? Plus this times twice tau12. Or more generally, if I do this for g variables, it's going to be the sum over, they're going to be g squared plus g over 2 variables, one for each entry on or above the diagonal of the gram matrices, and it's going to be the sum over g vectors of x pi I times the double sum over all j and k, this is a g here, of v, j, vk, tau, jk. That's why there is a factor of 2 here, because it counts tau 1, 2 as well as tau 2, 1. And so the variables here are tau jk, which are the same as tau kj, ranging from 1 to g. Okay. When does this converge? Convergence was easy in the one-dimensional case, so the just positive imaginary part. Here it's also positive imaginary part, but you have to tell imaginary part of what and positivity in what sense. And you form the imaginary part of the matrix tau jk, and you have to actually be positive in the sense of being positive definite. So here in the one-dimensional case, you are in the upper half space. Here this is the Ziegler upper half space. And this function again has various invariance properties. So for instance, we have translations of the tjk. Those, I mean, once you tell me what's the denominators of the rational numbers represented by q, it follows that translations of tau jk by any multiple of 1 over the denominator, any multiple of the denominator, maybe twice the denominator, preserves this thing here up to adding 2 pi I, and so these preserve this this Ziegler theta function of order g. And also we have a Poisson summation, except this time Poisson we have to go not over single vectors in the lattice, but Poisson in the g n-dimensional space, but that's okay, that's still a space that has a Poisson summation formula, and that, remarkably enough, takes tau to the matrix minus tau inverse. This is a symmetric matrix, so is this one, and that again takes the lattice to the dual lattice. You put these together, and you get something that is a modular form in a suitable sense that I'm not even going to pretend to exhibit here explicitly, but it's going to be a modular form for some congruent subgroup in the group generated by all of these translations, and tau goes to minus 1 over tau, which turns out to be the symplectic group of order 2g of 2G by 2G integer matrices. I remind you that if G equals 1, that is just the ordinary SL2, so it's almost what we know already, and I really should have put a projective here. So this does generalize, and there is this theory, of course it takes a long time to develop, but there is this theory of modular forms for the symplectic group or for congruent subgroups of it, and after a lot of work, you do eventually get results for at least large n. How large depends on the genus, but just like for theta functions, you just wanted this equidistribution of, if you just wanted estimates on representation numbers of quadratic forms, if n was large enough, and for one variable large enough with 3 or 4 or 5, depending on what kind of result you wanted, you got estimates. And here you still get estimates if n is bigger than basically some multiple of g. On the distribution, there are exactly which multiple depends on which method you use and how many theorems and conjectures you're willing to throw at it, but you do get results of this nature. And you get some further variations that you might not have seen in the one-dimensional case. For example, supposing that I have a lattice L that's not in Rn, it's in Cn over 2. So n is even. And Cn over 2, I have a Hermitian form. And suppose that any two lattice vectors have inner product, let's say, in the Gaussian numbers, or more generally, in some quadratic extension of Q. Well, in that case, you can regard L as a lattice over the integers by just having the inner product of any two vectors be the trace of this complex number. But if this lattice is actually a module for the ring of integers here, or for some order in it, like Manjul-Bhargava has been describing, you have some further structure here, and you couldn't possibly detect that structure if you just looked at theta functions of one variable, because if you just look at single vectors, all you can ever extract out of them is the norm, which is just the trace of this complex number, but this complex number is actually a real number. So you don't see anything new in this case. However, once you have two or more vectors that with configuration you're trying to measure, you actually have this Hermitian matrix which packs strictly more information than the gram matrix of the integral version of the lattice. And so in that case, again, you can construct even bigger, even more scary theta functions, which in this case would have 4 variables. In general, it would have g squared variables, but you can still throw them into some general machinery that describes modular forms and eventually get some estimates and allows you to get descriptions about embedding Hermitian forms or representing Hermitian forms by other Hermitian forms. And likewise, if you have a quaternionic form here, where this time each off-diagonal entry will consist of 4 real numbers instead of 2 or 1 as before. Okay, so finally, yes, all of this thing has weighted versions. So you can form Ziegler theta functions, let's say Ziegler theta functions of genus 2 of the lattice weighted by some periodic function of 2 variables multiplied by some harmonic function of 2 variables, harmonic function of 2 vectors. In principle, I mean, we know that these exist, and exist when we have a good enough theoretical handle on them, that we, and again, we means various people, not including myself, are able to get equidistribution results. Like if you look at all embeddings of equilateral triangles into the Leach lattice, as the size of the triangle gets larger, these triangles get equidistributed in the, what is it called? It's the Grassmannian of basically triangles in R24, of equilateral triangles in R24. But I wish somebody would tell me how to actually compute these polynomials, and therefore I more or less know how to compute Ziegler modular forms for the full modular groups, although even that's a pain in some part of the anatomy. And I wish somebody would bring this theory to a form where I can actually understand it well enough to make analogous computations and actually give you a formula for a number of these triangles in terms of presumably the tau function and some even more mysterious, coefficients of even more mysterious modular forms in two variables. At any rate, I think I've given you a few answers and enough questions, so maybe sometime before Arizona Winter School 10, some of them will be answered, but at any rate, that's all for me for this lecture series. Thanks again.